Good day, I am Dr. Ohlhoff and I will be discussing assignment 13 with you. So let's immediately start with the first problem. We have to use polar coordinates to evaluate the given integral. To do this, we have to find out exactly what the region D looks like so that we can also describe it in terms of polar coordinates. As you can see, D is a slice of a circle between the positive x-axis and the line x equals root of 3 times y, and the circle we have is x squared plus y squared is equal to 1. We also need to find the intersection of the line and the circle. As you can see, that is where x is equal to the root of 3 over 2 and y is equal to a half. This now allows us to see that the angle theta between the positive x-axis and the line x equals root of 3 times y is pi over 6. We can now describe the region D in polar coordinates quite easily. R has to go from 0 up to the edge of the circle of a radius 1, so R is between 0 and 1. And we measured, or we calculated, the maximum value of theta. So theta goes from 0 to pi over 6. We can now translate the integral in Cartesian coordinates to an integral in polar coordinates. Remember that we have to add the Jacobian, which is r in this case, underlined in red. In this case, the integrals are straightforward, so we leave that up to you to do. As you can see, the final answer is 1 divided by 120. That concludes the discussion of problem 1. In problem 2, we must use a double integral to find the volume of a solid inside a given cylinder above the xy plane and under the surface z equals root of x squared plus y squared. The first step is always to make a sketch. By rewriting the equation for the cylinder by completing the square, we find that this is a circle with radius 2 with center at the point where x is 2 and y is 0. This circle is shown by the sketch on the right hand side. The surface with equation z equals positive root of x squared plus y squared is the upper part of a cone as shown in the first sketch on the right hand side. We are going to use polar coordinates for our calculation, so we need to describe the circle on the right hand side in polar coordinates. As you can see, the boundaries for theta are pretty clear. Theta goes from negative pi over 2 to pi over 2, both endpoints included. To find the boundaries for r, we note that r must end on the circle x squared plus y squared equals 4x. Now, if you substitute the substitutions for polar coordinates, that translates to r equals 4 cos theta for r unequal to 0. Remember that x is r cos theta and y is r sin theta. So the boundaries for r are from 0 to 4 cos theta. We can now set up an integral to calculate the volume width. Remember that in general, the volume over a shallow area called r here is always the equation of the top surface minus the equation of the bottom surface. In this case, the bottom surface is the xy plane, which has the equation z equals 0. So the volume is simply given by the double integral over r of the top surface with equation z equals x squared plus y squared. We've also calculated the boundaries for r and theta, so we can translate this to the integral from negative pi over 2 to pi over 2. Those are the boundaries for theta, and the boundaries for r from 0 to 4 cos theta. The root of x squared plus y squared is r, and we also add another r, which is the Jacobian. You can check the various steps of the integration on your own. The only thing that may have caught some of the students was this here, cos to the power 3. And as you can see, the trick is to write cos to the power 3 as cos theta times cos squared theta. And cos squared theta is then equal to 1 minus sine squared of theta. You can do this with any uneven power of cos or sine if you have to find the integral. So you can check the rest of the calculations. The final answer is 256 divided by 9. That concludes the discussion of problem number 2. In problem number 3, you must use a suitable transformation to evaluate a given integral. The question always is, what is a suitable transformation? Let's have a look. As you can see, the curves that are given, as well as the integrand that is given, both contains the expressions x minus 2y and 3x minus y. It therefore makes sense to let u equals x minus 2y and v equals 3x minus y. Let's see what happens with the region R with this transformation. The first two given curves, namely x minus 2y equals 0 and x minus 2y equals 4, becomes u equals 0 and u equals 4. So u simply lies between 0 and 4, endpoints included. The curves 3x minus y equals 1 and 3x minus y equals 8 shows us that v lies between 1 and 8. For any transformation, we always need to find the Jacobian. In this instance, because of the way that we have set our transformation, u in terms of x and y and v in terms of x and y, it's easier to first calculate the Jacobian of the inverse, which gives us 5. So the actual Jacobian that we need, the Jacobian of uv, is 1 over 5. We now see that the double integral over r becomes the double integral over s. The integrand is now simply u divided by v, and you must always remember to add the Jacobian. We can now write the double integral as an iterated integral using the boundaries for u and v that we calculated previously. The integration is all pretty straightforward, so we leave it up to you to check the calculations. The final answer is 8 over 5 times ln of 8. That concludes our discussion of problem 3 and also of this assignment. Goodbye and good luck.